Interstellar visitor filters secrets. 3I Atlas reveals core of carbon dioxide in age of billions of years. No one expected that an object coming from another stellar system would show so many secrets guarded in its interior. Since its detection, the TR Atlas has puzzled astronomers from all over the world. What seemed like a simple passing visitor turned into a time capsule loaded with materials older than our own sun. And the most shocking part, its core composed of frozen carbon dioxide challenges everything we thought we knew about interstellar bodies. Every new observation, whether from the Hubble telescope or the powerful James Webb, reveals a new layer of mystery. Scientists now believe that 3I Atlas could have formed billions of years ago in the early days of its original stellar system. Its passage through our solar system is brief, but the clues it leaves could change the way we understand the formation of worlds. Today you will discover how astronomers deciphered the secrets hidden inside this visitor that comes from beyond the stars. What can a piece of cosmic ice teach us about the origins of the universe? Before we delve into the secrets of 3I Atlas, the interstellar visitor that revealed a core of frozen carbon dioxide and an age of billions of years, there are 3 things you need to do right now to engage the scientific community. First, please like this video to bring this discovery to more observers. Second, subscribe and turn on notifications to receive the latest updates on the real-time tracking. And third, go down to the comment section now and write 3I Atlas to join the global registry of those following this historic event. Please do this now. The 3 Atlas is a true cosmic intruder discovered by the Atlas Alert System in the year 2025. It was identified as the third interstellar object that crosses our cosmic neighborhood after Oumuamua in 2017 and 2E Borisov in 2019. But unlike them, this visitor showed from the beginning a very different behavior. A bright green coma, unexpected variations in brightness and a composition that does not fit with that of known comets from the solar system. Its hyperbolic trajectory confirms that it does not belong to our sun. It comes from another corner of the galaxy. It traveled for millions of years through the vacuum of interstellar space and by pure coincidence crossed our system in a fleeting encounter. Scientists take advantage of every second of observation to analyze its light, its spectrum, its dust and its gas. Everything that 3I Atlas shows from its core to its tail is invaluable information about planetary formation processes in other stellar systems. The more it is studied, the more questions arise. Why is its core formed by frozen carbon dioxide? What type of star launched it into space? And how long will it survive before disintegrating completely? Every answer obtained opens a new unknown. In this video we will explore step by step what science has revealed about this object that arrived from far away, but that is leaving a deep mark on modern astronomy. Everything began with a weak signal, a small spot in the data collected by the Atlas Alert System in Hawaii. It was the 12th of January 2025 and what at first seemed like a common object in motion, turned out to have a trajectory that did not fit with any known body in the solar system. Astronomers reviewed the calculations over and over again and the conclusion was clear. Its orbit was not closed. It was hyperbolic, which means that the object was not bound to the sun, it came from outside, from the depths of interstellar space. From that moment, the newly baptized 3I Atlas became the center of attention of observatories around the world. The Atlas telescopes, Pan-STARRS, Subaru and Gemini were the first to record its movements. As the weeks passed, more instruments joined the observation. The Hubble Space Telescope, the Very Large Telescope in Chile and finally the James Webb Space Telescope, that from its position at point L2 offered a privileged view? All confirmed the same thing. 3I Atlas was not a typical comet. Its brightness varied irregularly. Its color turned green in certain wavelengths and its tail, if it could be called that, seemed to form and disappear in a matter of days. Unlike Oumuamua, which showed no clear signs of sublimation, and 2E Borisov, which did behave like a classic comet, the 3 Atlas seemed to be situated between both cases. It was not completely inert, but neither did it decompose like common comets. Scientists began to analyze its spectrum in detail, separating the light it reflected to identify the chemical compounds present. It was then that the first surprise emerged: carbon dioxide. In the spectrum, clear lines corresponding to frozen carbon dioxide were detected, something extremely rare in interstellar comets. In the solar system, comets are usually dominated by water, carbon monoxide or methane, but the predominance of carbon dioxide indicates that the environment where this object formed was much colder, possibly in the outer regions of a very distant planetary system. This finding completely changed the interpretation of the object. It was not just a piece of icy rock wandering aimlessly, but a preserved fragment of another stellar system, a direct testimony of the chemical diversity of the galaxy. As the data accumulated, researchers noticed that the coma, the gaseous envelope surrounding the core, showed a characteristic green tone. This color is usually related to diatomic carbon molecules CO₂, which excite upon receiving solar radiation and emit light in the visible range. However, the intensity of that emission in 3I Atlas was unusually high, suggesting an anomalous concentration of these compounds. This raised new questions about the formation process of the object. Could it have arisen in a region where carbon was much more abundant than in our own system? The Hubble confirmed, in addition, that the size of the core was small with an estimated radius less than 3 kilometers. This data is crucial because it indicates that despite its brightness, the object was not massive. Its glow came mainly from the gases that evaporated as it approached the Sun. And yet, those emissions were not constant, they varied in intensity unpredictably. Astronomers from the Institute of Astrophysics of Andalusia proposed that perhaps the 3 Atlas was slowly fragmenting, releasing pieces of material that momentarily increased its brightness before disintegrating. Meanwhile, teams from NASA and ESA crossed data from different observatories. The orbit confirmed that the object came from a direction opposite to the movement of the Sun in the Milky Way, implying that it traveled from a region completely alien to our stellar neighborhood. It was estimated that it had spent at least 1 million years crossing interstellar space exposed to constant cosmic radiation bombardment, which would explain the partial blackening of its surface. That outer layer, hardened by centuries of exposure, could have sealed the inner ice, preserving its original composition intact. The James Webb, with its ability to observe in infrared, allowed looking beyond the surface. Its spectra revealed that the core contained not only carbon dioxide, but also traces of carbon monoxide and simple organic compounds. This was an extraordinary discovery because it indicates that the molecules essential for prebiotic chemistry, the one that precedes life, are not exclusive to our system. If in the first planetary systems of the galaxy bodies with this type of compounds were formed, the possibility that life arises in other places increases considerably. Comparisons with Borisov and Oumuamua became inevitable, unlike the first, which had a composition rich in cyanides and water, and the second that never showed visible gas. 3 Atlas represented a middle point that provided new clues. Its behavior seemed to demonstrate that interstellar objects are more diverse than thought and that each one comes from completely different environments. The chemical history of the 3I Atlas became a puzzle that scientists are still trying to solve. As it approached perihelion, the closest point to the Sun, at the end of October 2025, its activity increased. Observatory cameras captured a sudden expansion of the coma and the object gained brightness for several days. Social networks filled with images and headlines that exaggerated the phenomenon, talking about explosion or enormous increase in size, but scientific data showed another reality. What happened was a release of gases and dust as the core heated, a normal process in icy bodies. Public interest grew impressively. For the first time in years, millions of people looked back at the sky searching for that small green point that crossed between the constellations. Astronomers took advantage of the moment to explain the importance of studying these visitors. Each one of them is a unique opportunity to understand how planets, comets, and ultimately the ingredients of life are formed. Over the following months, spectroscopic analyses continued to confirm the presence of carbon dioxide and organic materials. Researchers published their results in specialized journals, highlighting that this object represents an intact sample of the primordial material that exists beyond our system. Every atom in its interior tells an ancient story, prior to the formation of Earth. The confirmation of its interstellar nature was the first big step. The second and perhaps the most fascinating was discovering that it carried chemical signals from other solar systems. What for the human eye is just a flash in the firmament. For science it is an open window to the remote past of the cosmos. The 3 Atlas not only passed near us, it left an indelible mark on the history of modern astronomy. Its secrets began to unveil little by little, as if the universe itself had wanted to remind us that it still holds many enigmas to explore. When astronomers confirmed that the 3I Atlas contained large amounts of frozen carbon dioxide, the finding surprised even the most experienced. In most solar system comets, the main volatile component is frozen water accompanied by carbon monoxide, methane, and silicate dust. However, carbon dioxide is not usually dominant, since it requires extremely low temperatures to remain solid for so long. Its massive presence in the 3I Atlas suggests that this object formed in an environment much colder and more distant than the one that gave rise to our own system. The instruments of the James Webb Space Telescope were essential to detect that gas. Thanks to its ability to observe in infrared wavelengths, the JWST can distinguish the absorption and emission patterns characteristic of different molecules. When sunlight hits the 3E atlas, part of that radiation is reflected and part is absorbed by the gases that evaporate. Analyzing those spectral fingerprints, scientists can know exactly what compounds are present. In this case, the carbon dioxide signature was so clear that there were no doubts. This discovery has profound implications. For carbon dioxide to remain stable in solid state for billions of years, the object must have formed in a region located much beyond the so-called snow line of its original system. In simple terms, the snow line is the distance from a star from which volatile compounds can freeze. In our solar system, that line is beyond the orbit of Jupiter. And the 3I Atlas was born in an even colder zone. It probably orbited a type M or K star, weaker and older than the Sun, where temperatures in protoplanetary disks are extremely low. The composition of the 3I Atlas also indicates that it was sealed for eons without suffering significant heating. Unlike comets that periodically travel near the Sun, interstellar objects do not experience cycles of sublimation and refreezing. Its surface remains exposed to the absolute cold of space, reaching temperatures close to -260 degrees Celsius. Under those conditions, carbon dioxide molecules remain trapped in the ice, forming a solid matrix that preserves information about the primordial chemistry of the environment where planets formed. The comparative analysis with the data from 2E Borisov reinforced this interpretation. While Borisov showed a composition more similar to comets from the Kuiper belt with predominance of cyanides and water, the 3I Atlas offered a more exotic mixture. The JWST spectra revealed that carbon dioxide was accompanied by traces of carbon monoxide and simple organic compounds such as formaldehyde H2CO and methanol CH3OH. These compounds are considered precursors of more complex molecules, capable of participating in reactions that lead to the formation of amino acids. The finding generated enthusiasm in the scientific community because it reinforces the idea that complex organic chemistry is common in the cosmos. If the basic building blocks of life can be found in bodies formed in other stellar systems, then the process that gave rise to life on Earth could repeat in countless worlds. It is not about speculating on extraterrestrial life, but about understanding that the fundamental ingredients are present in many corners of the galaxy. Researchers also studied the isotopic proportion of carbon in the 3E Atlas. Measuring the ratio between carbon-12 and carbon-13 isotopes allows estimating the age of the material and the type of environment in which it formed. The results indicated that the 3I Atlas preserves an isotopic signature different from that of solar system comets, demonstrating that its origin is indeed interstellar. That chemical fingerprint works like a cosmic passport, unequivocal evidence that the object was born in a system that has nothing to do with ours. While the James Webb observed variations in carbon dioxide emission, as the object approached the Sun, scientists were able to build three-dimensional models of its structure. They discovered that gas release was not uniform, but concentrated in specific points of the core. This means that the surface of the 3I Atlas has fractures or active regions where solar heat penetrates more easily, causing ice sublimation. Those regions could be ancient cracks originated during its expulsion from the natal system, when some collision or gravitational instability launched it into interstellar space. The data from Hubble and the Subaru telescope complemented this information, showing that the amount of dust released along with carbon dioxide was relatively low. This implies that the core is composed mainly of pure ice with very little rock or solid material. In other words, the 3I Atlas is not an asteroid covered in ice, but an almost complete icy mass. A witness to the coldest and most primitive conditions of planetary formation. The green color that characterizes its coma is due in part to the interaction of carbon dioxide with solar radiation. When carbon dioxide decomposes under ultraviolet light, it generates carbon radicals that emit greenish light. This phenomenon, known as molecular fluorescence, is one of the reasons why carbon-rich comets show such vivid tones. In the case of the 3E Atlas, the color intensity is so strong that it can be observed even with medium telescopes. Something very unusual for an interstellar object. Another aspect that caught attention was the shape of its emission. Observations from the VLT in Chile indicated that the gas escaped in opposite directions, creating an effect known as anti-coma. This type of structure appears when particles emitted by the core are pushed toward the Sun due to the orientation of the object and solar radiation pressure. The anti-coma of the 3I Atlas became one of the most commented images of 2025 and helped calculate its rotation speed. Astronomers estimated that the object spins on itself every 7 or 8 hours. a fairly fast pace for its size. That rotation contributes to the intermittent release of gas, generating the brightness changes that caused so many headlines. But far from being an explosion or a sudden growth in size, the phenomenon responds to the natural dynamics of an icy core that reacts to the sun's heat for the first time in millions of years. The study of carbon dioxide in 3 Atlas also provides valuable information on how comets form in general. In protoplanetary disks, carbon dioxide freezes at temperatures less than -80 Kelvin. In those regions, dust grains are coated with ice layers that contain this gas. If a stellar system suffers gravitational disturbances, some of those icy blocks can be expelled into interstellar space. Thus, the 3I Atlas would be one of the countless fragments that wander the galaxy, carrying the chemical signature of its mother star. Simulations indicate that each star could have expelled millions of these objects throughout its history. Most will never be detected, but a few, like the 3I Atlas, cross our path. Observing them is like receiving an ancient message from another corner of the universe written in the language of chemistry. Every carbon dioxide molecule, every trace of methanol or formaldehyde tells a part of that story. The combination of all these findings has allowed building a detailed image of the 3I Atlases, a frozen traveler, formed in the coldest regions of a distant system and preserved for billions of years. Its frozen carbon dioxide composition not only differentiates it from local comets, but turns it into an authentic sample of the primordial material that circulates through the galaxy. Thanks to it, scientists can directly compare the chemistry of our solar system with that of other systems, something that until recently seemed impossible. And although its passage will be brief, the information it leaves will be studied for decades. The carbon dioxide that composes it becomes a silent witness of time and distance, a footprint of the cold and the processes that gave rise to worlds. In that small icy body traveling beyond the limits of the sun, science finds a tangible connection with the cosmic past. Determining the age of an interstellar object like the 3I Atlas is not an easy task. There are no direct methods to date its origin, but science has tools capable of estimating its antiquity through chemical composition, surface degradation, and prolonged exposure to cosmic radiation. Every atom in its structure keeps a story, and in this case that story dates back to the dawn of the galaxy itself. Astronomers began by analyzing the type of ice present in the core. Frozen carbon dioxide accompanied by traces of methane and carbon monoxide suggests that the 3I Atlas formed in an extremely young environment, when the first generations of stars were still producing the heavy elements necessary to form planets and comets. These compounds solidify only in regions where the temperature drops below -50 Kelvin, implying that its system of origin was in an early stage of evolution. The isotopic study of carbon, oxygen, and nitrogen was key. The results showed proportions that differ notably from those observed in solar system bodies. In particular, the ratio between carbon-12 and carbon-13 points to an older environment, where nucleosynthesis, the process by which stars create new elements, was still in development. In other words, the material that composes the 3I Atlas could come from a generation of stars prior to the one that formed the Sun. If this is confirmed, we would be facing a fragment of matter that has existed for more than 5 billion years. The time spent in interstellar space leaves unmistakable marks. The surface of the 3I Atlas has been exposed to high-energy cosmic radiation for millions of centuries. That exposure produces chemical changes in the ice, darkening its color and hardening its texture. This process, known as cosmic spallation, slowly transforms the outer layers of the material, generating complex organic compounds that act as a protective armor. The surface layer of just a few centimeters absorbs most of the damage, preserving the inner ice in its original state. The James Webb data confirmed the existence of that aged crust. By analyzing the infrared light reflected by the object, scientists detected a spectral signature corresponding to polymerized organic molecules. These form when ultraviolet radiation and energetic particles impact the ice over long periods. The most fascinating thing is that the density of that layer suggests a minimum exposure of 1 billion years, possibly more. This result coincides with simulations that estimate that a body expelled from its natal system can wander the galaxy between 1 billion and 10 billion years before encountering another stellar system. The fact that the 3I Atlas has preserved its structure after such a journey is a testimony to the stability of ice in extreme vacuum. In the absence of collisions and heat, matter can survive almost indefinitely. Over that time, the object would have crossed regions of the galaxy with different densities of gas, dust, and radiation, acquiring a rough surface and a slightly modified chemical composition. Its age, therefore, not only reflects the time since its formation, but also its resistance to the interstellar environment. Computational models created by the Harvard Center for Astrophysics and the Max Planck Institute in Germany showed that if an object with the characteristics of the 3I Atlas had been expelled from a solar system 4,500,000,000 years ago, its current orbit would be very similar to the observed one. This is due to the gravitational influence of stars and molecular clouds it has encountered along its journey. Each subtle encounter modifies its trajectory, giving it that hyperbolic movement that now directs it out of the solar system. The analysis of the dust surrounding the object also provides clues about its age. The particles emitted by the 3 Atlas have an extremely small size of just a few microns. This indicates that the material has suffered erosion for billions of years, fragmenting until reaching that fineness. If the object were younger, the dust would be thicker and more reflective. Instead, the dust from 3I Atlas shows a dull shine, consistent with where caused by time and radiation. Another indication comes from its thermal behavior. When approaching the Sun, heat should penetrate slowly toward the interior, causing a gradual release of gases. However, measurements showed that the 3I Atlas reacts more slowly than expected, as if its surface acted as an insulating shield. This can only be explained if the outer layer has been hardened by millions of years of cosmic bombardment, reducing its thermal conductivity. That shell of aged matter is one of the strongest proofs of its antiquity. On an astronomical level, an object of this age is equivalent to a time capsule. Its composition reflects the chemical conditions of the interstellar gas at the time when the first planetary systems of the Milky Way formed. Studying it is like looking back in time, to the moment when essential elements, carbon, oxygen, nitrogen, began to combine to form more complex molecules. Scientists have compared its study to analyzing a cosmic fossil, a relic that has crossed millennia to reach us. The 3 Atlas also allowed testing models on the evolution of interstellar material. Simulations suggest that dust grains expelled by supernovae and stellar winds slowly condense in protoplanetary disks where they give rise to icy planetesimals. Some of these bodies, when disturbed by giant planets or stellar migration, are expelled into outer space. Over the eons, these fragments wander the galaxy, becoming messengers from their systems of origin. The 3 Atlas would be one of those messengers formed when the galaxy was still in its youth. The study of its age also has implications for understanding the solar system itself. If the 3 Atlas and the Sun have comparable ages, it means that both arose from gas clouds with similar chemical composition. In other words, the basic materials of which the 3I Atlas is made could be the same that formed the planets and comets of our neighborhood. This reinforces the idea that planetary formation processes are universal and that cosmic ingredients are widely distributed throughout the galaxy. Observing its faint glow from observatories in Chile and the Canary Islands, astronomers know they are seeing something that existed long before humanity, even before Earth solidified. It is a silent, ancient presence that travels space with the patience of centuries. Its core, frozen and hardened, has survived the passage of time in an almost poetic way. A fragment of another stellar dawn, traveling without destination, carrying the memory of the cosmos. Every spectrum, every light measurement, every brightness curve of the 3I Atlas is data that connects us with that story. When telescopes capture its weak reflection, the signal that reaches our instruments is not just a point in motion, but tangible evidence that the universe preserves traces of its own past. Thus, the 3 Atlas not only tells us where it comes from, but also how long it has existed and how it has survived in its long journey through the stars. And while it continues to move slowly away, scientists continue analyzing the collected data. Every adjustment in the models confirms the magnitude of its age. The 3I Atlas may soon disappear from our telescopes, but the knowledge it leaves will endure because in that small frozen visitor, humanity has found a living proof of the antiquity and permanence of matter in the cosmos. When the 3I Atlas was identified for the first time, its trajectory already showed something that made it completely different from any other known object. Its orbit did not describe a closed ellipse like that of planets or common comets, but a hyperbolic curve. That means its speed is greater than necessary to remain trapped by the Sun's gravity. In other words, it did not come to stay. It entered, crossed the solar system and will soon leave again toward interstellar space. This simple characteristic was already enough to confirm its external origin, but the details of its path revealed much more. The first calculations by astronomers showed that the 3I Atlas was approaching from a region of the sky near the constellation of Hercules. It was moving at more than 26 kilometers per second with respect to the Sun, a speed sufficient to cover the distance between Earth and the Moon in just 4 hours. Its approach angle indicated that it had crossed the galactic plane millions of years ago, traveling from a direction completely alien to the rotation of our galaxy. That means that from a cosmic point of view it moves against the current like a traveler swimming upstream. As it approached, observatories around the world recalculated its orbit with greater precision. It was determined that its perihelion, the closest point to the Sun, would occur between the 29th and the 30th of October 2025. At that moment it would pass at a distance of just over 0.8 astronomical units from the Sun, that is, slightly inside Earth's orbit. This offered a unique opportunity. Its brightness would increase enough to be observed even with medium telescopes, allowing to study its behavior in real time. During its approach, images captured from Chile, Hawaii and the Canary Islands showed a small object, greenish in tone and with a faint tail. But the most interesting was the direction of that tail. Instead of pointing directly opposite to the Sun as happens with traditional comets, in some shots the tail seemed oriented at a strange angle. This phenomenon known as anticoma occurs when the heaviest particles emitted by the core are dragged in a direction opposite to expected due to the angle between Earth's line of sight and the object's orbital plane. It is a purely geometric effect, but in the case of the 3I Atlas it gave rise to impressive images that fueled public curiosity. Astronomers also observed sudden variations in its brightness. During the month prior to perihelion, the object almost doubled its luminosity in a matter of days to then decrease again. These changes could be due to irregular gas release as different areas of the core heated. Every time a crack or fracture opened, the inner ice sublimated, releasing carbon dioxide and dust into space. That momentary ejection increased the reflective surface, producing the effect of a temporary flash. The passage through perihelion was the most anticipated moment. On the nights of the 29th and 30th of October, the 3I Atlas reached its maximum activity. Its coma expanded to cover more than 100,000 kilometers in diameter and the anticoma visually extended for several million kilometers. Spectra obtained by the James Webb confirmed a significant increase in the amount of carbon dioxide released. However, no signs of fragmentation or explosion were detected. The object remained stable, although temporarily brighter. That stability surprised many researchers who expected such a small and icy core to disintegrate under solar heat. After perihelion, the 3I Atlas began its departure from the Sun. Radiation decreased, ice stopped sublimating and the coma slowly dissipated. Subaru telescope observations showed that in a matter of weeks brightness fell almost in half. It was as if the visitor wrapped itself again in its mantle of cosmic silence, ready to continue its solitary journey. Despite its rapid departure, the brief encounter left a treasure of data for science. During its passage, its trajectory was followed with such precision that it allowed calculating its entry and exit point from the solar system with an error margin of just a few kilometers. The results showed that it entered above the plane of the planets and will exit below, crossing near Mars' orbit and then Jupiter's to finally head toward the constellation of Shield in the direction of the outer edge of the Milky Way. That route will take it out of reach of our telescopes in a few years, slowly disappearing among the stars. The study of its speed also provided revealing data. Astronomers calculated that before entering the solar system, its relative speed with respect to the Sun was about 26 kilometers per second. After its passage, due to solar gravitational pull, it increased slightly to about 42 kilometers per second. That acceleration will push it even further, ensuring it never returns. Its path is definitive, an open line toward immensity. The passage of the 3I Atlas was also used to make comparisons with space missions. Some researchers imagined what it would have been like to send a probe to intercept it, in the same way as planned for future interstellar objects. However, its speed and short notice time made any approach attempt impossible. Still, the collected data serve as a basis for designing future rapid response missions. NASA is already working on concepts of spacecraft capable of launching in a few months to intercept similar visitors when detected. During its stay in the inner solar system, it was also studied how solar radiation affected its structure. It was discovered that the object did not rotate uniformly, but with a slight wobble like a spinning top starting to lose balance. That irregular movement could be the result of its asymmetric shape or uneven gas release. Over time, that wobble could cause stresses on its surface, generating small fractures that would release more gas in the future. Another important point was the comparison between its brightness before and after perihelion. Data showed that the 3I Atlas did not lose significant mass during its passage, meaning its internal structure is compact and resistant. This detail contradicts the idea that interstellar objects are fragile or unstable. On the contrary, the 3I atlas demonstrated unexpected solidity capable of withstanding a solar approach without disintegrating. Scientists also took the opportunity to measure how it interacted with the solar wind. Using satellites equipped with particle detectors like SOHO and Stereo, it was observed how the object's gas flows were deflected by the sun's magnetic field, forming a small magnetotail. This phenomenon, observed for the first time in an interstellar body, allowed studying how solar plasma influences materials of extragalactic origin. Throughout its journey, the 3I atlas was photographed hundreds of times. The most detailed images come from the Very Large Telescope in Hubble, which recorded the evolution of its coma and color. By comparing those photographs, one can see how the green intensity varied depending on the distance to the sun. These variations correlate directly with the amount of carbon dioxide released, confirming that its core is dominated by that gas. While humanity observed it for the last time from ground telescopes, astronomers reflected on the nature of its journey. This object had wandered for billions of years before spending a few brief months in our neighborhood. Now it will return to the darkness of interstellar space, where it will perhaps spend as many more millennia before encountering another stellar system. Its passage through the solar system was fleeting, but it left a deep impact. It demonstrated that we are not isolated, that fragments of other worlds cross our path and connect us with the vast network of systems that make up our galaxy. Thus, the 3 atlas continues its way, moving further from the sun every day. Its light weakens, but its scientific legacy grows with each analysis. And although it will soon disappear from our telescopes, the traces of its passage will remain engraved in the data, in the studies, and in the memory of all those who for a brief instant observed it crossing the sky like a messenger from the stars. During the months that the 3I atlas remained under observation, one of the greatest unknowns was the irregularity of its brightness. Unlike common comets, which follow a relatively predictable pattern, increasing luminosity as they approach the sun and decreasing it as they move away, the 3I atlas showed sudden, unpredictable oscillations and sometimes disproportionate. In a matter of hours it could become almost twice as bright to then fade to the point of seeming stable again. This behavior puzzled astronomers and generated headlines around the world. However, science soon began to find explanations based on the physics and chemistry of its core. The first clue came from Pan-STARRS telescope observations. The data showed that the brightness increase coincided with a subtle change in the shape of the coma. At some moments the 3I atlas seemed to expand its gaseous envelope, releasing a cloud of particles that reflected more sunlight. This phenomenon occurs when heat penetrates a crack in the core, causing a small gas eruption. In solar system comets this process is known as outburst or sublimation burst. What differentiates the 3I atlas is that these outbursts did not follow a regular pattern. They seem to depend on the object's rotation and its uneven exposure to the sun. Astronomers from the Institute of Astrophysics of the Canary Islands noted that each sudden brightness increase lasted just a few hours or at most, 1 or 2 days. Then the object returned to its normal luminosity. This suggests that it was not fragmentations or collisions, but temporary releases of gas and dust from active zones. These gas explosions can occur when heat reaches carbon dioxide deposits buried under denser layers of ice or organic material. Upon evaporating, the gas escapes forcefully, dragging dust into space and briefly increasing the comet's reflectivity. Spectroscopic observations from Hubble and James Webb confirmed this theory. During brightness peaks, the spectrum showed a sudden increase in carbon dioxide emissions, accompanied by greater light scattering in the visible range. This means that the 3I atlas was not disintegrating but breathing. Each luminosity increase was a cosmic exhalation. The gas accumulated under the surface found an outlet and expanded into the vacuum. Despite this physical explanation, the object's behavior remained peculiar due to its intensity. Some outbursts were so energetic that for brief periods the 3I atlas seemed to shine like a much larger comet. Astronomers estimated that at those moments it expelled up to 100 tons of gas and dust per second. However, that amount decreased rapidly, indicating that activity was concentrated in very localized areas of the core, perhaps in cracks opened by thermal stress. The thermal analysis performed through computational models revealed that the core of the 3I atlas is not uniform. It presents zones of different density and composition, causing solar heat to penetrate unevenly. In the most compact regions, ice remains stable. In the more porous ones, gas is released easily. This internal mosaic of materials could explain the variations in activity. Each rotation of the object would expose different areas to the sun, activating some while others cool. Rotation precisely is another key factor. Very large telescope observations showed that the 3I atlas has a rotation period of about 8 hours, although not completely regular. There is evidence of slight wobble or precession, as if the object rotated on an unstable axis. That irregular movement causes variations in solar illumination, activating different core zones unpredictably. Thus, each brightness pulse would be the result of the interaction between rotation, internal structure, and solar heating. A second complementary cause was also proposed: surface fragmentation. Although there were no indications that the core split into large pieces, it is possible that small outer layers detached due to heat, releasing fine dust that reflected sunlight with great efficiency. This phenomenon known as surface shedding has been observed in comets like 67P Churyumov-Gerasimenko, visited by the Rosetta probe. In the case of the 3E atlas, brightness variations would be the visual manifestation of those microscopic processes. The object's optical behavior was monitored by automatic telescope networks around the world. Thanks to those measurements, scientists were able to build detailed light curves showing luminosity changes as a function of time. Those curves revealed an interesting pattern. Outbursts seemed to coincide with moments when the object was in specific positions in its orbit. Just when solar radiation reached a critical angle on its surface, this reinforces the idea that emissions were controlled by differential heating. In the media, some headlines claimed that the 3I atlas had exploded or increased its size suddenly, but scientific data do not support such claims. What was observed was a series of natural brightness variations typical of a body composed mainly of ice. The word explosion may sound spectacular, but in reality it describes a controlled and transient phenomenon. Comets, especially those containing carbon dioxide, are prone to this type of activity because carbon dioxide sublimes at relatively low temperatures. During the period of maximum activity, the James Webb also detected a cloud of fine particles surrounding the object. These particles, probably composed of silicates and amorphous carbon, are so small that they scatter sunlight efficiently, producing a diffuse brightness effect. Over time, that cloud expanded and dispersed, causing overall brightness to decrease again. In this way, the 3 atlas went through several cycles of luminosity increase and decrease, each with slightly different characteristics. Another important finding was the correlation between the object's color and its activity. During brightness peaks, the green tone of the coma intensified, indicating greater production of diatomic carbon, C2, and cyanogen, CN2 molecules common in cometary atmospheres. This suggests that eruptions also released volatile organic materials along with carbon dioxide. In other words, the light flashes of the 3I atlas were not only visually spectacular, but chemically revealing. As the object moved away from the sun, those variations became less frequent. Heat decreased, gases stopped sublimating, and the core regained its calm. However, the data obtained during that period of intense activity are essential to understand how interstellar objects react upon contact with solar energy after eons in darkness. For the first time, astronomers were able to directly observe how a body formed in another stellar system responds to the heat of our star. The detailed study of light curves will allow in the future to deduce the internal structure of its core. From the intervals between brightness peaks, scientists can infer the distribution of cavities, fractures, and active zones within the object. It is work similar to that of a geologist studying a volcano's heartbeats to understand its underground anatomy. In this case, the eruption is of ice and gas, and the laboratory is hundreds of millions of kilometers away. The brightness variations of the 3E atlas, far from being an unexplained mystery, have become a valuable tool to understand the physics of interstellar bodies. Each luminosity change tells a story about its temperature, rotation, and composition. And although headlines spoke of explosions, scientific reality is even more fascinating. The 3 atlas breathes, adapts, and reacts to the sun like an ancient being that awakens after a sleep of billions of years. Its light, changing and unpredictable, is not a sign of destruction, but of physical life in its purest form. Matter that responds to energy following the laws of the universe. And in those fleeting flashes, astronomers read fragments of the history of its system of origin encoded in the dance of its brightness. From its stable position at the gravitational equilibrium point L2 1,500,000 kilometers from Earth, the James Webb Space Telescope became the key instrument to study the 3E atlas, with a level of detail that no ground observatory could match. Its ability to observe in the infrared spectrum allowed scientists to look beyond visible glow and penetrate the molecular structure of the object. Thanks to its NIRPEC and MIRI instruments, the Webb achieved the most complete chemical fingerprint ever obtained from an interstellar visitor. The first observations confirmed what optical telescopes already suspected. The 3 Atlas was not a rocky body, but a complex mixture of ice, dust and organic compounds. But what the Webb revealed was even more impressive. In the spectral data, characteristic peaks of carbon dioxide, CO₂, carbon monoxide, CO, methane, CH4, ammonia, NH3 and traces of formaldehyde, H2CO appeared. This combination suggests that the 3I Atlas formed in an extremely cold environment where even the most volatile gases could freeze. The simultaneous presence of methane and formaldehyde is particularly relevant, since both are precursors of more complex organic molecules, essential for prebiotic chemistry. The team from the Goddard Institute of NASA analyzed the data and found something more. Weak but consistent signals of polycyclic aromatic hydrocarbons. These molecules composed of carbon and hydrogen rings are considered one of the basic components of interstellar organic matter. They form in the atmospheres of dying stars and spread throughout the galaxy, later integrating into molecular clouds where new stars and planets are born. Finding them in the 3I Atlas means that this object carries material recycled from previous generations of stars, becoming a chemical archive of the cosmic cycle of matter. The Webb data also allowed estimating the surface temperature of the 3I Atlas during its close passage to the Sun. At perihelion it reached about 220 Kelvin, equivalent to -53 degrees Celsius. Although it seems a low temperature, it was enough to activate sublimation of carbon dioxide and methane. However, the surprising thing is that water ice remained mostly stable, confirming that its core is composed of more volatile materials. This unusual behavior explains why its coma remained green and carbon-rich, but without showing typical water vapor emission peaks. The Webb's precision even allowed observing slight variations in the coma's composition over time. During the weeks prior to perihelion, the spectrum showed predominance of carbon dioxide and methane, but as it approached the Sun more notable traces of nitrogenated compounds appeared. This suggests that the object's surface is stratified. The outer layers exposed to space for millions of years contain a different mixture than the interior, richer in nitrogen. Those composition differences are valuable clues about the formation process of the object in its natal system. The James Webb also allowed observing the dynamics of gas around the core. Using high-resolution spectroscopy, scientists were able to measure the speed of gas escaping into space. Carbon dioxide jets reaching up to 500 meters per second were recorded, a huge speed considering the core's weak gravity. Those jets explain the temporary expansion of the coma and the brightness changes observed from Earth. The fascinating thing is that the jets were not constant, but intermittent, suggesting that the 3I Atlas has irregularly distributed active zones like valves that release gas when heated. In addition to analyzing its composition, the Webb measured the texture and reflectivity of the dust accompanying the gas. It was discovered that particles had an average size of 0.2 microns, extremely fine, and that they were composed mostly of amorphous carbon and silicates. These characteristics match the type of dust found in young protoplanetary disks. In other words, the material expelled by the 3I Atlas is very similar to that which gave rise to planets and moons and other stellar systems. Observing it is like witnessing on a microscopic scale the raw material of world creation. Another relevant finding was the thermal distribution of the coma. As the object approached the Sun, the Webb detected a temperature gradient extending from 220 K near the core to about 150 K in the outer regions. This gradient demonstrates that gas cools rapidly as it moves away, forming a tenuous and temporary atmosphere that dissipates in a matter of days. The study of that process allows better understanding of how comets, even those of interstellar origin, interact with the solar environment and how their material disperses in interplanetary space. The use of the Webb also provided information on the exact size of the core. Through direct observations in infrared, astronomers estimated a radius of just 2.5 kilometers with a very low albedo, that is, a surface that reflects little light. This means that the 3I Atlas is dark, covered with carbonized organic materials that absorb radiation. That dark layer acts as insulation, preventing heat from penetrating rapidly and controlling the sublimation rate. This detail explains why the object was able to preserve its structure without disintegrating despite its closeness to the Sun. The data collected by the James Webb were combined with those obtained by the Hubble telescope and ground observatories, creating a three-dimensional portrait of the 3 Atlas. Thanks to that collaboration, scientists were able to reconstruct its approximate shape. An elongated core with a major axis of about 5 kilometers and a minor axis of about 2. Its irregular shape favors its chaotic rotation and localized gas outbursts, which makes sense of the previously recorded brightness variations. But perhaps the most transcendental aspect of the Webb observations was its contribution to the study of the object's interstellar origin. Analyzing the isotopic proportion of oxygen and carbon, scientists confirmed that it does not match any group of solar system comets. Its values are closer to those detected in star formation regions located in the constellation of Orion more than 1,000 light-years away. This does not mean that the 3I Atlas comes specifically from there, but that its composition is representative of young interstellar material enriched by supernova explosions. The Webb also detected a surprising characteristic, a faint sodium emission in the near-infrared visible range. This element found in many solar system bodies is rarely observed in such cold objects. Its presence indicates that the 3I Atlas has suffered slight surface heating during its journey, possibly by passing near other stars before entering our system. Each interstellar encounter would have subtly modified its surface without altering its interior. The legacy of the James Webb observations is immense. Thanks to them, humanity has for the first time a detailed record of the chemistry and structure of an object coming from another stellar system. Each obtained spectrum represents a capsule of information about the environment where it was born. These data will help compare planetary formation processes in different systems and determine if the distribution of organic and volatile compounds is a common phenomenon in the galaxy. When astronomers review the Webb graphs, what they see are simple lines and color peaks. They see the chemical signature of a world that existed far from here, long before Earth had oceans. They see proof that the ingredients of life, carbon, hydrogen, oxygen and nitrogen, circulate freely among the stars. And in that sense, the 3I Atlas is not just a visitor, but a messenger that confirms the deep connection between all corners of the cosmos. The passage of the 3I Atlas through our solar system was much more than a simple astronomical curiosity. It became a natural laboratory to study how planetary systems form and evolve throughout the galaxy. Every data collected by telescopes, from gas composition to orbital dynamics, has allowed comparing the object's chemistry with that of comets from our own system. And those comparisons offer a powerful conclusion. Planetary formation processes seem to repeat in many places in the universe, although each system has its own chemical signature. One of the main lessons is that the 3I Atlas contains the same fundamental elements as solar system comets: carbon, hydrogen, oxygen, and nitrogen. However, the proportions are different. In it, carbon dioxide dominates over water, suggesting that it formed in a much colder environment. This indicates that its mother star must have been less luminous than the Sun, perhaps a red dwarf or a Type K star. In those systems, the so-called snow line, where gases freeze to form ice, is closer to the star, allowing volatile material to accumulate more easily. The comparative study has also demonstrated that the organic chemistry of the 3I Atlas is surprisingly rich. The compounds detected by the James Webb, methane, formaldehyde and traces of complex hydrocarbons, are the same that scientists have observed in young protoplanetary disks of other stars. This means that prebiotic chemistry, that is, the one that precedes the formation of biological molecules, is not exclusive to the solar system. The 3I Atlas acts as a chemical ambassador that confirms that the basic ingredients of life are scattered throughout the galaxy. The fact that this interstellar object has traveled for billions of years and still preserves those compounds demonstrates the stability of those molecules in interstellar space. Scientists believe that ice acts as a protective capsule, preserving organic matter against cosmic radiation. This durability suggests that life's building blocks could survive the journey between stars, something that strengthens theories like panspermia, although without affirming it speculatively. What can be said with scientific certainty is that organic elements are common and resistant, and that changes the perspective on the distribution of living matter in the universe. The 3 Atlas also teaches about the diversity of stellar systems. While solar system comets show a relatively constant proportion between water, ice, and dust, this visitor presents a composition dominated by more volatile gases, indicating different conditions at its origin. This confirms that each planetary system can have its own thermal and chemical balance determined by the mass, temperature, and age of its star. Some can produce water-rich comets, others carbon dioxide or methane. By comparing these patterns, astronomers can infer the characteristics of the systems where those bodies formed. The isotopic analysis has also revealed that the 3I Atlas comes from a region of the galaxy with a stellar history different from ours. The proportions of carbon and oxygen in its core match measurements in molecular clouds located in the Orion arm. This does not imply that it comes exactly from there, but suggests that it was born in an environment enriched by recent supernovae, where heavy elements were more abundant. That type of environment favors the formation of complex molecules and organic-rich planetary systems. In this sense, the 3I Atlas is a direct sample of how ancient stars contribute to seeding the universe with ingredients for new worlds. Observations have also allowed testing models on how matter is distributed within protoplanetary disks. Dust grains and ices tend to separate according to their size and density, concentrating in different zones of the disk. The fact that the 3I Atlas has a small core rich in carbon dioxide indicates that it probably formed in an outer region where condensation was slow and pressure low. This helps calibrate the models that astronomers use to study planet and comet formation in other stellar systems observed by telescopes like ALMA or the Webb itself. Another important lesson is about the frequency with which these objects travel between systems. With the discovery of 1E Oumuamua, 2E Borisov and now 3 Atlas, scientists have calculated that the galaxy could contain trillions of wandering interstellar bodies. Most are too small and dark to be detected, but each stellar system during its formation expels thousands of these fragments into space. That means that material exchange between systems is not rare, but a natural part of the cosmic cycle. Our own solar system could also be sending fragments toward neighboring stars, some of which, in millions of years, could be observed from other worlds as interstellar visitors. From a scientific point of view, this reinforces the idea of an interconnected galaxy, where matter flows from one system to another. Expelled comets and planetesimals act as messengers that carry chemical, physical and mineralogical information from their systems of origin. The 3I Atlas is just one of them, but its study demonstrates that the boundary between our solar system and the rest of the galaxy is more porous than we imagined. In a sense, all stellar systems are communicated by the constant exchange of matter. Observations also offer information on the thermal and mechanical stability of these bodies. The 3I Atlas proved to be more resistant than expected, withstanding passage near the Sun without fragmenting. This suggests that its internal structure is dense and cohesive, possibly composed of ice layers mixed with organic compounds and compressed dust. That type of structure could be common among objects formed in outer regions of systems, where collisions are less violent and materials remain compact. Knowing that resistance helps engineers design future missions that can intercept or sample interstellar bodies without destroying them. Another learning comes from the interaction of the 3I Atlas with the solar wind. During its passage, SOHO satellite instruments detected disturbances in the flow of charged particles around the object. This allowed studying how solar plasma affects organic compounds and how radiation can alter their molecular structure. The results showed that although part of the material ionizes, most molecules resist the impact, confirming the high stability of carbon compounds in extreme conditions. The scientific legacy of the 3I Atlas goes beyond its chemical composition. It offers a direct view of how cosmic processes connect on a galactic scale. What happens in a stellar system is not confined there. Material can travel, mix and seed other systems. From that continuous exchange arises the diversity we observe in exoplanets, moons and comets. Each interstellar visitor is a page torn from another cosmic book that upon crossing with us allows us to read a part of its story. The 3 Atlas also inspires new lines of research. Astronomers plan to develop automatic detection programs to identify future visitors with greater advance. The objective is to send robotic missions that can approach them before they move away. In the case of the 3E Atlas, the Webb and Hubble data have already served to design models on how to capture complete spectra of fast-passing objects, something that will be crucial in upcoming encounters. In summary, this interstellar visitor has demonstrated that solar systems are not isolated islands, but points within a galactic network where matter circulates freely. Its carbon-rich composition and resistance to solar heat teach us that the processes that gave rise to life here can repeat in many places. Every atom in its core is a testimony to the universal power of cosmic chemistry, a confirmation that life, in its most fundamental sense as organized matter, could have roots throughout the galaxy. And thus, while the 3I Atlas continues moving away toward deep space, it leaves behind an invaluable legacy. The certainty that we are not chemically or physically isolated from the rest of the cosmos. We are part of a vast exchange of matter, an eternal cycle that unites all stars through the dust, ice and comets that silently cross between them. When astronomers thought they had understood the activity pattern of the 3 Atlas, new observations revealed behaviors that did not quite fit with the expected. Its luminosity, color and coma orientation showed variations that went beyond traditional cometary models. Although there was no doubt of its interstellar nature, scientists began to realize that this visitor was in many ways, an unprecedented type of object. Neither Oumuamua nor Borisov had shown such a complex combination of physical and dynamic characteristics. One of the most surprising aspects was the intensity of the green color of its coma. In common comets, the greenish tone is due to diatomic carbon molecules C2 and cyanogen, Cn, which excite under solar radiation and emit visible light at that wavelength. However, in the 3 Atlas, the concentration of these molecules was so high that its brightness surpassed at times that of much larger comets. Some astronomers suggested that the object's chemical composition favors a more efficient production of these compounds, perhaps by carbon dioxide decomposition in the presence of ultraviolet radiation. Others, however, considered that its core could have deposits especially rich in carbon, which would explain the chromatic intensity. The variability of the coma also caught attention. In a matter of days, the gaseous envelope changed shape, size, and orientation. Subaru telescope images showed an asymmetric structure, a kind of plume that extended in a direction different from the main tail. This is interpreted as evidence of localized gas jets expelled from active regions of the core. Those jets, upon being released with different intensities, caused the object to experience slight alterations in its rotation, also affecting its trajectory. The dynamic behavior of the 3I Atlas was studied in great detail. Data from the Very Large Telescope and Lowell Observatory showed small variations in its apparent speed on the order of a few millimeters per second. Although they seem insignificant, these changes are relevant to understand how gas jets can act as natural thrusters. In the case of the 3E Atlas, intermittent carbon dioxide outbursts exerted constant pressure that slightly altered its movement. In the same way that happened with Oumuamua, whose acceleration change generated so many discussions in 2017. But unlike that case, in the 3I Atlas there are spectral data that confirm the presence of gases, so the cause is perfectly explainable through cometary physics. The analysis of its rotation yielded equally fascinating results. Observations indicate that its rotation period, initially estimated at about 8 hours, varied slightly over time. During the approach to the Sun, the period shortened to about 7 hours and a half and then lengthened again upon moving away. This effect, known as jet acceleration, occurs when gas emission modifies the body's angular momentum. The 3I Atlas behaved in a sense like a gyroscope that changes its rhythm as it releases energy. The shape of the object is also a crucial factor to explain its behavior. Models built from Hubble and James Webb data suggest that the core of the 3I Atlas has an elongated and irregular figure with an axis ratio of approximately 2.1. This geometry causes solar heating not to be uniform. Some zones receive more radiation than others, generating internal thermal stresses that favor the appearance of cracks and uneven gas emission. In addition, irregular rotation contributes to different parts of the core activating at different times, which explains the brightness variations and coma shape. Another peculiar phenomenon was the appearance of a very marked anticoma during perihelion. In traditional comets, the anticoma forms when the heaviest particles emitted by the core lag behind the direction of the solar wind and from Earth's point of view seem to project toward the Sun. However, in the case of the 3 Atlas, this structure was more defined and persistent than usual. Its orientation changed slowly over several weeks and its length reached unusually large values. Astronomers used dust-scattering models to simulate the phenomenon and concluded that the emitted particles had an extremely small size, on the order of 0.1 microns, which allowed them to remain in suspension longer. Fluctuations in the gas flow surrounding the core were also detected. Using high-resolution spectra, researchers measured different speeds in different directions, as if gas escaped from several active points simultaneously. This type of behavior, although observed in other comets, had never been documented so clearly in an interstellar object. The presence of multiple active sources suggests a complex internal structure, perhaps the result of a history of collisions or thermal differentiation processes in its original system. The 3I Atlas also surprised by its structural stability. Despite violent temperature changes and intense solar radiation, the object showed no signs of significant fragmentation. Some researchers expected it to partially disintegrate upon reaching perihelion, but subsequent images showed it remained intact. This indicates that its internal composition is more compact than anticipated, with sufficient cohesion to resist thermal stresses. This resistance can be explained if its core contains a high proportion of solid organic compounds mixed with ice, acting as a natural glue that holds the material together. The optical behavior also offered unprecedented details. Unlike most comets, the 3I Atlas did not show a gradual transition between different brightness states, but abrupt jumps. Astronomers described it as an impulsive object whose calm phases were interrupted by brief periods of great activity. Each outburst released a gas cloud that expanded rapidly and then dissipated, returning the object to its original luminosity. This repetitive cycle gives the impression that the comet breathes, alternating between exhalations and silences, a dynamic that symbolizes its living nature within the physical laws of the cosmos. Scientists also observed a curious detail. After perihelion, the 3 Atlas slightly changed its color, adopting a more bluish tone. This could be due to the sublimation of the most superficial carbon-rich layers, exposing fresher material, possibly with greater content of carbon monoxide and methane. That chromatic change is a sign of accelerated aging, since passage through the solar system irreversibly altered its surface. When it returns to interstellar cold, it will carry with it the traces of the Sun, a thermal scar that will slowly modify its composition over the eons. Throughout its entire study, astronomers insisted on an essential point. The 3I Atlas does not behave anomalously because it is strange or mysterious, but because it represents a type of body that we had never had the opportunity to observe up close. It is a product of different conditions, of a chemical and thermal history alien to that of our system. What seems atypical to us in its system of origin could be common. That idea changed the way scientists conceive interstellar objects, not as rarities, but as pieces of a larger mosaic that reflects the diversity of the galaxy. In this sense, the 3I Atlas has taught us that normality in astronomy depends on the point of reference. Each interstellar visitor expands the limits of what we understand as natural behavior. Its own, with its intense green tones, persistent anti-coma, unpredictable outbursts and surprising stability, represents a new category within icy bodies. It is a reminder that nature does not repeat exactly and that variety is one of the most constant laws of the universe. The study of the 3E Atlas, still ongoing, continues to challenge conventional cometary models. Every collected data adds a piece to a cosmic puzzle that encompasses not only our solar system, but the systems that exist beyond. And although the visitor is already slowly moving away toward darkness, its atypical behaviors continue to illuminate our understanding of how bodies born under other stars act. After perihelion, when the Atlas began its slow departure from the Sun, a feeling of nostalgia swept through the astronomical community. 4 months, that interstellar visitor had been the undisputed protagonist of scientific observation, a messenger from other stars that offered answers and at the same time new questions. Now, as its brightness diminished and its coma faded, astronomers prepared to follow it to the confines of the solar system, before it disappeared forever into the darkness of interstellar space. The first weeks after perihelion showed a notable change in its behavior. The intensity of sunlight reaching the 3I Atlas decreased, and with it also the sublimation activity. The bright green coma, which had made it famous, began to shrink, in carbon dioxide emissions, which during maximum approach had reached their highest point, became sporadic. Telescopes recorded an increasingly weak gaseous envelope, while the core regained its silent appearance, as if the object, after its brief encounter with the Sun, returned to an ancestral state of rest. Despite its growing distance, the James Webb and Hubble continued observing it for several additional weeks. The data showed a progressive drop in brightness and a reduction in surface temperature that returned to values close to -150 Kelvin, about -120 degrees Celsius. Under those conditions, gas stopped flowing and ice sealed again. It was as if the visitor closed the doors of its interior before departing back to eternal cold. The object, which had been so active and energetic, transformed again into a sleeping ice rock, advancing without destination toward the galactic abyss. The trajectory of the 3 Atlas was calculated with enormous precision by teams around the world. With combined data from observatories in Chile, Hawaii, the Canary Islands and space, astronomers determined that its exit orbit has an eccentricity greater than 1, confirming its definitive hyperbolic character. This means it will never return. Its escape speed is so high that no gravitational field in the solar system can retain it. At its farthest point it will reach speeds close to 42 kilometers per second, sufficient to completely abandon the Sun's influence and head toward the galaxy's periphery. On its exit journey, the 3 Atlas passed at a safe distance from Mars' orbit and then approached the asteroid belt, where telescopes could still follow it. There, amid the rocks and icy bodies orbiting between Mars and Jupiter, its passage was barely perceptible, a weak point reflecting sunlight without showing its characteristic green glow anymore. However, its detection continued to be a technical feat. Every captured photon was a fragment of the history of a body that will not cross our path again. As it moved away, Jupiter's gravity exerted a subtle influence on its trajectory. Although the gas giant failed to capture it, its gravitational field slightly altered its course, giving it a final push outward. This final interaction was studied in detail, since orbital dynamics models show that encounters with massive planets can modify the orientation of the hyperbolic trajectory. In this way, the 3I Atlas said goodbye to the solar system with a small deviation, as if Jupiter itself had pushed it toward its new destination. Scientific interest did not end with its departure. Researchers then began the phase of deep analysis, comparing the data collected during its passage with those obtained from other interstellar objects. Observations of its coma, color, and composition were transformed into models that will allow in the future to more easily identify new visitors. The 3 Atlas thus became a reference, a Rosetta Stone to decipher the chemical and dynamic codes of interstellar bodies that may arrive in the coming decades. Meanwhile, in observatories, some astronomers continued pointing their telescopes toward the ever fainter point where it was located. Over the months, its brightness fell below the visible limit, even for large aperture telescopes. At that moment, it ceased to be a directly observable object and passed to exist only as coordinates and numbers in astronomical databases. But every recorded figure represented an achievement, a confirmation that we had witnessed the passage of something coming from another stellar system, a traveler that crossed our sky for a brief instant on the cosmic time scale. The last measurements showed that its coma had disappeared completely. What remained was a dark and silent core of about 2.5 kilometers in diameter, slowly rotating on its axis as it moved away toward the outer regions of the solar system. Without more reflected light, without visible tails, the 3 Atlas became undetectable, losing itself among the stellar background. Its passage marked the end of an observation stage and the beginning of an era of reflection. Scientists, upon reviewing the data, understood that this object represented much more than an astronomical rarity. It was a tangible symbol of the connection between worlds. From an emotional point of view, its departure evoked the feeling of farewell that accompanies great discoveries. The 3 Atlas had been for a short period an open window to the remote past of the cosmos. It had revealed fragments of its chemistry, shown its carbon dioxide core, and allowed humanity's most advanced telescopes to study a piece of matter formed under another sun. Now, that same body was moving away without looking back, returning to the silence that had accompanied it for billions of years before reaching us. Scientists calculated that in less than 2 years its brightness will be so weak that no existing telescope will be able to detect it. By then it will be beyond Jupiter's orbit, heading to the outer regions dominated by solar wind. Beyond that point, it will cross the heliosphere limit, where solar particles no longer dominate space and the realm of the interstellar medium begins. There the 3 Atlas will again be part of its natural element, the cold and silent darkness between stars. However, its legacy will continue alive. The spectroscopic data from James Webb and Hubble will continue to be analyzed for years. Every spectral line, every light curve, every brightness variation will become valuable information for models attempting to understand the formation and evolution of stellar systems. Thanks to this visitor, scientists have been able to confirm that the materials composing worlds are not exclusive to one system or star. They are universal, circulate, mix and transform in the eternal cycle of cosmic matter. The 3E Atlas, although small and ephemeral on our scale, left us a lesson of greatness. It reminded us that the limits of the solar system are not closed borders, but open doors to the galaxy's paths, that matter travels, that worlds share their essence, and that the history of our sun is written with the same atoms that one day formed other suns. And thus, while its faint silhouette is lost forever in vastness, the 3 Atlas leaves behind a heritage of knowledge and wonder. Its farewell is not a definitive goodbye, but a promise, that of new interstellar travelers crossing our sky, bringing with them the secrets of places where we have not yet arrived. Each one of them will remind us that the universe is a continuous ocean and that we, observers on a small blue planet, have only just peered over its shore. When the 3I Atlas vanished from telescopes and its light stopped reflecting on detectors, its journey through the solar system ended, but the true impact was just beginning. What it had left behind was not just a trail of gas and dust, but an indelible mark on the history of modern astronomy. Every observation, every spectrum, every brightness measurement became a piece of a puzzle that continues to expand our understanding of the cosmos. The 3I Atlas was not just a fleeting visitor but a time capsule, a witness to how interstellar matter moves, evolves and preserves over billions of years. The scientific legacy of the 3 Atlas can be summarized in 3 great contributions. Its confirmation as a genuinely interstellar object, the discovery of a core dominated by carbon dioxide and the verification that complex organic compounds are widely distributed throughout the galaxy. Those three truths transformed the study of icy bodies and opened new lines of research that go far beyond this specific object. The first great achievement was to consolidate the concept of interstellar archaeology. With the arrival of Oumuamua in 2017 and Borisov in 2019, the scientific community had understood that interstellar objects existed, but did not know how frequent or varied they could be. The 3 Atlas, with its intermediate behavior between both previous cases, demonstrated that the diversity of these bodies is enormous. Some are rocky, others icy, some inactive, and others tremendously volatile. Together, these interstellar visitors reveal that each stellar system produces a wide range of planetesimals that can escape into space and travel the galaxy, carrying with them the chemical signature of their origin. The study of the 3 Atlas also drove a technological revolution. Continuous tracking of the object required international coordination and simultaneous use of latest-generation instruments, from the most powerful ground telescopes like the VLT and Subaru, to space observatories Hubble and James Webb. This cooperation allowed establishing protocols that now serve as a model for the detection and observation of future interstellar visitors. Algorithms capable of automatically analyzing data from alert systems like Atlas and Pan-STARRS were created and issuing instant notifications to research teams around the world. In this way, the legacy of the 3 Atlas is not only scientific but also organizational. It changed the way humanity reacts to the arrival of objects from other stellar systems. From a chemical point of view, its contributions were even more transcendent. James Webb observations showed that the 3I Atlas was composed largely of frozen carbon dioxide, accompanied by methane, carbon monoxide, and organic compounds. This combination is different from that of any solar system comet, confirming that its formation environment was colder and more distant than ours. In addition, the finding of polycyclic aromatic hydrocarbons, complex molecules associated with the origin of organic matter, reinforced the idea that prebiotic chemistry is not a terrestrial exception, but a common process in the universe. These results also have implications for the study of exoplanets. If interstellar comets transport organic material across the galaxy, they could contribute to enriching young systems with the ingredients necessary for the formation of complex molecules. Some scientists propose that this continuous material exchange, a kind of cosmic pollination, could accelerate chemical processes that in certain worlds end up giving rise to life. Although it is not a speculative claim, the data from the 3I Atlas support the idea that basic components are present and active in multiple regions of the Milky Way. Another aspect of the legacy of the 3I Atlas lies in its physical resistance. The fact that it survived its passage through perihelion without fragmenting demonstrates that interstellar bodies can be more compact and cohesive than thought. This observation challenges traditional models that predicted rapid disintegration due to solar heating. Now it is known that some of these objects possess an internal structure reinforced by organic compounds and densely compressed ice, allowing them to withstand higher temperatures. This discovery will be crucial for the design of future space missions intended to intercept or study an interstellar object up close, as it provides data on material resistance and its behavior under solar radiation. In addition, the passage of the 3 Atlas left a deep cultural mark around the world. Its green brightness was followed by amateurs, school observatories, and scientific outreach communities. On social networks, millions of people shared images, simulations, and articles about its origin. For a few months, all humanity looked back at the sky, fascinated by the idea that a fragment of another solar system was crossing our neighborhood. This phenomenon of global interest helped bring astronomy closer to the public, reminding that the universe is not a distant stage, but a living and moving space of which we are part. The 3I Atlas also established a new frontier for astrobiology. The collected data on its composition demonstrate that essential ingredients for life, carbon, oxygen, nitrogen, and hydrogen, not only form in abundance, but can survive intact for billions of years in interstellar space. This finding gives empirical support to models proposing that life, or at least its chemical components, could be the inevitable result of cosmic evolution. If organic matter is so resistant and so common, then each stellar system has the potential to develop on its own terms the processes that one day led to the appearance of organisms on Earth. The effects of its study even extend to education and outreach. Universities around the world have incorporated the 3I Atlas as a case study in astrophysics, planetary chemistry, and cosmology courses. Students learn how spectroscopy methods, orbital dynamics and computational modeling are combined to decipher the secrets of an object that was barely observed for a few months. In this way, the legacy of the 3I Atlas is not limited to the acquired knowledge, but inspires new generations of scientists to continue exploring the universe with the same curiosity that drove its discovery. The international scientific community has also recognized the importance of preparing future missions. From the lessons learned with the 3 Atlas, proposals are being developed for rapid interception probes capable of studying interstellar bodies in real time. These missions that could launch in the next decade will combine high-efficiency engines with advanced spectroscopy instruments and will be capable of reaching newly detected objects before they move too far away. NASA and ESA have declared that the observation of the 3I Atlas was a dress rehearsal for the new era of interstellar exploration. The passage of the 3 Atlas, however brief, has marked a dividing line in the history of astronomy. Before it, interstellar objects were a theoretical curiosity, afterward they are a priority research field. Its study has not only allowed better understanding of planetary formation processes, but has also reinforced a fundamental idea. The universe is an interconnected system. The matter that forms stars, planets, comets and eventually life flows from one corner to another, uniting the entire galaxy in a continuous cycle of creation and transformation. When the 3 Atlas disappeared from our instruments, it was not lost. Its history remained recorded in scientific archives. In the images captured by the Webb, in the light graphs from Hubble, in the articles detailing every detected molecule. Every stored data is a seed of knowledge that will germinate in future discoveries. In the silence of space, the 3I Atlas continues traveling, carrying with it the memory of its encounter with the Sun and with the humanity that observed it. And although no one can see it anymore, its legacy continues to shine. Because the 3 Atlas not only showed us what worlds are made of, but also what our curiosity is made of, the eternal need to look beyond, to understand the unknown, to seek in the stars the answers to our own origin. In that sense, this interstellar visitor fulfilled the deepest mission that a scientific discovery can have. Reminding us that we are part of something much larger, a universe in constant dialogue with itself.